Hello, everyone. Yes, my name is Marc Fassbender. I'm one of Marc Henton's PhD students at the University of Ottawa, and I use the chemistry, petrology, machine learning to investigate modern ocean settings, such as the one that Marc just highlighted to you. So we still hope that we can better understand ancient greenstone belts by investigating modern ocean settings. So in this talk, we will explore the systematics of felsic volcanic rocks in interoceanic regimes, such as the lava basin that we saw before and the Manos basin. And we will compare them to samples from the Archean Abitibi greenstone belt. So why am I doing that? As basically all of you know, felsic volcanic rocks are intimately associated with volcanogenic massive sulfide deposits, and that resulted in the well-known F classification scheme of rhyolites, which became one of the most important geochemical exploration tools that exists. And it's based on the idea that the depth of felsic metal lenses can be monitored using rare earth elements. So basically, deep felsic metal lenses are associated with high pressure mineral phases such as garnet and amphibole, which preferentially incorporate HRE, and that results in the steeply dipping RE pattern. And in contrast, shallow metal lenses are obviously not associated with these high pressure mineral phases, and they have flat RE patterns. So the F classification reflects this depth relationship, in F1 being associated with deep metal lenses, F2 being associated with intermediate metal lenses, and F3 being associated with shallow metal lenses. And importantly, the F3 signature has been subdivided into F3A and F3B, of which F3B is a particular perspective and very strongly associated with Archean environments. So what we want to do is we want to understand how this classification holds up in modern oceanic regimes, and if these are comparable, and if they are, what can we learn from that? So we started off creating a database. This is a database containing felsic volcanic rocks in various submarine environments. This compilation has no more than 2,000 samples, and it covers ocean islands, mid-ocean ridges, ridge hotspot intersections, and various arc assemblages as well. This database was then screened for samples that are completely analyzed in major elements such as silica, alumina, titanium, potassium, and trace elements such as thorium, barium, niobium, lanthanum, zirconium, and ytterbium. And we have chosen those elements based on the significance they have in various lithotectonic environments, their usage in geochemical discrimination diagrams, and obviously their availability in our data sets. So this final data set now contains 645 samples. Those samples have been used to investigate the geochemical systematics here. And we started off using a test diagram as we are used to in modern oceanic regimes, and Winchester and Floyd, as we do for altered and Archean environments. And we see that samples from ocean islands have low Si2 concentrations, that have high sodium potassium concentrations, and that is reflected in high niobium yttrium ratios, as well. And ridge hotspot intersections are slightly more transitional. They have ferritic samples as well. They have high Si2 concentrations, slightly lower sodium potassium concentrations, and that is again reflected in decreasing niobium yttrium ratios. Our samples from mid-ocean ridges have by far the lowest Si2 concentrations. They have low sodium potassium concentrations, and once again, this is reflected in decreasing niobium yttrium ratios as well, but they still have high zirconium titanium oxide ratios. And arc and back arc samples have by far the largest spread in Si2 concentrations. They have the largest spread in sodium potassium concentrations as well. And obviously that is once again reflected in the niobium yttrium ratios and the zirconium over titanium ratios too. So these in general geochemical trends are reflected in the trace element pattern as well. So for example, here for hotspots, samples from Hawaii and Samoa, for example, they have these steeply dipping RE pattern. They're generally enriched in incompatible elements such as niobium and thorium, and especially rich hotspot samples like those from Iceland or Ascension Island and Azores have strong negative European anomalies. The dacite from mid-ocean ridges have generally flat RE pattern, They do not have any negative niobium tantalum anomaly, but they do have negative europium anomaly. So here we have sums from the Hu and the Fuca Ridge, the Pacific Rise, and Galapagos that we just saw before. And our last end member basically are arc and near arc volcanoes. These have these strong pronounced negative niobium tantalum anomalies. They have kind of flat RE pattern as well, but they do not have, or if they do, it's very weak. These very weak to almost absent negative europium anomalies. So these very simple systematics here become surprisingly complicated as soon as we are investigating back-arc environments. And you just saw this one. This is the Lau back-arc basin, which kindly Marc already introduced, so I don't have to do that anymore. It opened around 6 million years ago, and it has several spreading regimes, which part of them we already saw. So we have the Wall of Far Ridge down here with a few Felsic samples, the central Law spreading center here with the Felsic samples, and the northwestern Law spreading center here. And those spreading centers occur in various distances to the arc, which is great because we can actually monitor how the arc influences those melting regimes. So obviously they are controlled by the arc. We have fluids which are derived from the dehydrating subducted slab. And that causes those Felsic melts from the Wall of Far Ridge to have these strong negative niobium tantalum anomalies. They have overall low RE concentrations, flat RE pattern, and very weak negative europium anomalies. In contrast, the samples from the central Law spreading center and the northwestern Law spreading center here have overall high concentrations in RE. They do have negative europium anomalies, and the negative niobium tantalum anomaly basically completely disappears. So it's important that even within one of those large lithotectonic environments, we have multiple and quite diverse geochemical signatures. So we wanted to investigate the heterogenetic control mechanisms here as well. And we wanted to use some statistical machine learning techniques too. And so we used principal component analysis to investigate our data structure. And principal component analysis, or short PCA, is a data transformation technique. It's nothing new at all. It's been around for more than 100 years, but it's been increasingly used in recent years, and so did we. So what it does, it reduces all the variables, so all these elements here, into a number of components, and each of those components is affected by all the variables. So here we have 13 elements, hence we have 13 principal components, of which the first principal component is affected by, or visualizes the most variance in the data set, and the last principal component visualizes the least variance in the data set. So here we have PC1 and PC2 visualized in the biplot. So these elements here, those variables, are loadings, and that helps us because basically any of those samples which plots close to one of those elements is stronger affected by one of those elements. We see some kind of clustering. So we have Ocean Island and Ridge hotspot intersections plotting in the upper left corner. We have mid-ocean ridge like rocks in the upper right corner, interoceanic arc and back-arc samples in the lower right corner, and intercontinental arc and back-arc samples in the lower left corner. So there's some kind of clustering that we see, but we don't want to cluster them ourselves. We want to have that unbiased too. So we use agglomerative Ruckel clustering for that. And that clustering basically assumes right at the beginning that each sample forms its own cluster. So we have 645 samples. Hence, right at the beginning, we have 645 clusters. And then via proximity matrix, the distances from one cluster to another cluster is calculated. And the two samples with the smallest distance are incorporated in the next level of cluster. So this procedure goes on and on and on until all clusters are actually incorporated in one final cluster. And from that, we can retrieve a data tree, which is great because we actually can investigate how many clusters are representative for our data set. So in our case, that's 9 clusters. And for example, the cluster C1 here and C2. incorporate ocean islands and rich hotspot intersection samples, which reflects enrichment in incompatible elements such as niobium and lanthanum. Cluster C3 contains all the mid-ocean ridge rocks, and it is reflected for increased HRE concentrations, which is due to assimilation of oceanic or hydrated oceanic crust. And then we have interoceanic arc and backup samples down here in the lower right corner, reflecting enrichment by fluids released from the bucket dehydrating slab. And the same is true for the intracontinental samples in the lower left corner, but those are furthermore affected by assimilation of continental crust. However, I really want to highlight that this cluster here contains only or contains all of the mid-ocean ridge rocks. So this is a very consistent and very unique geochemical signature, but it incorporates a few back arc spreading center samples as well. So those samples are plotting in the southern central Laos spreading center, in the northern northwestern Laos spreading center, and at the Mangatolo triple junction. And the geochemical signature of those are seemingly identical to those in mid-ocean ridges. In fact, they are identical, except that any sample from backup environments, and Crystal just highlighted that, have the potential to be preserved, while any true mid-ocean ridge dacite or rhyolite will undergo subduction at some point, and it will be lost to the geological record. Furthermore, we can have them in relatively close spatial distance to arc-related rocks, like in the Mangatolo triple junction, because the first spreading center is actually focusing a lot of the wet melts, while the second spreading center behind stays almost dry. So what I really wanted to mention here and highlight here is that our geological record is obviously strongly biased, and that becomes even more evident as soon as we are starting to plot our samples in the F classification. So here, after Hart et al. 2004, we see that certain lithotectonic environments occupy certain F classes. So F1 and F2 is occupied mostly by ocean islands and rich hotspot sections. So do the intracontinental related samples, and intraoceanic arc and back arc samples occupy mostly F3A and F4. However, those mid-ocean ridge rocks and mid-ocean ridge-like rocks are plotting close to or even within the F3B array. And I want to mention again that this HRE enriched signature is very strongly tied to alkaline environments. So for example, here we have a few samples from Kamoskasia, Matagami, and Kid Creek, and all of them plot close to or within that array. And especially samples from Matagami here in green have the chemical signature that seems almost like samples from the northwestern Lao spreading center, so on the northwestern part of the Lao basin. We further want to verify those similarities. So we went back to our PCA results here and created a random forest classification scheme. So in that case, random forest is trained to identify those 9 clusters or those 9 target classes by training. So training is basically an iterative process by which random forest learns which values are meaningful to achieve the best separation outcome. And in our case, we use 80% of our data as a training data set and 20% of our data as a validation set. So that one is just to test our results to see that our classifier is actually doing a good job. Our random forest has 1,000 decision trees, and each of those is being trained by 3 randomly selected elements like samarium, yttrium, and ytteria, for example. And it's not a black box. We can investigate it, and we should investigate it, like in that case here. So overall, the best classification outcome highly depends in our case for those dacites and rhyolites based on alumina, barium, niobium, thorium, and ytterium, yttrium, which totally makes sense, right? So we have barium, for example. Any arc-related rock is strongly enriched in barium, which is released by subducted, which is released by fluids released from the subducted dehydrating slab. We also saw the strong negative niobium tantalum anomalies in arc-related environments, so it makes sense as niobium is incorporated here as well. And Iteria as an HRE, we have those mid-ocean ridge-like environments which are strongly enriched in HRE due to assimilation of hydrated oceanic crust. So this is perfectly in agreement with what we saw already. So since we have this classifier, we applied it for some samples in the Abitibi greenstone belt. And that confirms a number of similarities that we just saw before, like metagamy, for example, which belongs here to target class 3. Target class 3 is this mid-ocean ridge-like cluster. And here we have Kid Creek, which has been identified as target class 2. Target class 2 contained many of the ridge hotspot sections, so samples from Iceland and Black River and Noranda, which have much more diverse geochemical signatures, but most of them, or many of them, are associated with target class 5, which is a cluster that we see in the Manus Basin all the time. And yeah, so in summary, mid-ocean ridge-like dacite in complex microplate mosaics, like in the northern Lau Basin as we saw them before, and the Manus Basin, they're always related to enormously high heat flow, rising hot asthenospheric mantle, and they are related to complex spreading regimes. And these are potentially very important for preservation. The rocks that we see there have strong similarities with archean F3B-like rocks, such as those from metagamy, for example. They're obviously not exact tectonic analogs, but many processes here that are responsible for those chemical signatures might be very important in archean greenstone belts as well. Furthermore, we confirm a number of similarities that have been mentioned in other studies before, like those from Kid Creek to Iceland, or the Manus Basin to the Noranda district. And we think that major differences that we see between archean and post-archean ferrovolcanic rocks could be explained by differences in their preservation potential, so the kind of lithotectonic environment in which they occur. And last, but certainly not least, we think it's absolutely very likely that we will see many more additional comparisons between modern and ancient greenstone belts in the upcoming future, because this study would not have been possible a few years ago because we absolutely lacked those samples to make that comparison. So the ocean floor is still being explored basically as we speak, and with that more samples are retrieved. So it seems very likely that we will see more similarities in the upcoming future. Yeah, that's it. Thank you very much.
Thank you very much, Mark. We do have time for 1 or 2 questions.
I have a question. Mark, I liked your presentation very much. I'm curious about the principal component analysis, and did you transform the data before you did that principal component? And if you did transform, what kind of transform did you use?
Yeah, so we transformed the data. We used centered log ratio transformation. And prior to applying that, we also checked the database for outliers.
Right, okay. And then when you showed the results of your random forest classification, your chart showing the significance of the elements, I'm curious as to whether the random forest was carried out on the CLR transformed elements, or were they done on the principal components?
Oh no, it was done based on the centered log ratio transformed data and not on the principal components. So we did not run, well, we did, but not for testing our random forest classification. It was not run on the PCA results in the Abitibi, but it was only run on centered log ratio transformed data from the Abitibi.
Right. Well, I'm wondering if using the principal components might be a better way of doing the random forest classification, because you can sort of increase your signal to noise with the principal components. So just something to consider. Anyway, thank you. It was a great presentation.
Thank you.